Welcome to Oddly Real. I'm Nem Stefanovic. In this episode, we discuss the famous number pi. Most of us are somewhat familiar with pi because in school we've had to calculate the circumference of a circle, or maybe it was part of a formula you learned in a calculus class, or maybe you heard a story in the news that a supercomputer broke a record calculating the latest digit of the number. In any case, it might not be clear to you why pi is such an important value. If you stick around, I'll show you that it's oddly more interesting than it might seem. To start, pi has been known for thousands of years, since the times of antiquity, among multiple ancient civilizations. I won't go into the history of pi, but I will say that pi gives a very important foundation for mathematics, science, and engineering. Specifically, pi is defined as the ratio of the length of the circumference of a circle to the length of its diameter. This relationship is not an arbitrary human construct. In fact, it is foundational to spatial geometry. A circle itself is a fundamental and unique geometric shape. So if a circle is involved in some work or a calculation, it is not surprising to see the number pi appear. Another aspect about circles is that when you traverse a circle around its circumference, you return to the starting point where you are then able to begin a new traversal. Many phenomena in nature consist of cycles that repeat themselves. We can model these cyclical processes based on the traversal of a circular path. For example, a radio station frequency can be modeled with a sinusoidal waveform that oscillates in hertz or cycles per second. Alternatively, these types of waveforms can also be represented in frequencies of 2 pi radians per second. It's very common to see the number pi appear in cyclical repeating processes. The number pi itself has some interesting properties. It's what's called an irrational number. That means you cannot construct pi as a ratio of 2 integers. That in itself is a little ironic, since the very definition of pi is a simple ratio, but I digress. It also means that the digits in the number pi do not cycle or repeat themselves in a fixed pattern over time. The digits in the number go on forever in a single long unique sequence of values. That also means that you can't actually write down the number pi, at least not in its entirety, using the decimal number notation. There are many organizations in the world that are using very advanced algorithms combined with supercomputers in an effort to find more digits in the number pi. Well over 100 trillion digits of pi have been discovered, and more are being discovered every day. In fact, if you wrote down a string of digits for the known values of pi using a 10-point font, the digits would reach from planet Earth to somewhere between Uranus and Neptune in our solar system. That's a lot of digits of pi and a lot of accuracy. You might wonder why, aside from human curiosity, would someone want to calculate pi to so many digits of accuracy? It turns out that there are practical uses for knowing these digits. They can be used to perform test comparisons on supercomputers or tests against new numerical analysis algorithms. There's a deeper meaning to the value of pi and what it means for the geometry of space itself. I'd like to illustrate with an example. We start from the definition of pi, the ratio of the circumference of a circle to its diameter. Here, pi is a constant. It is invariant and does not change for any circle wherever it is located for any size of circle. We can rewrite this relationship to illustrate the point differently, as c, the circumference, is equal to pi times d, the diameter. Any change in diameter d produces a proportional change in length of circumference by pi. So if we start with a diameter of 0, then the circumference would also be 0. That makes sense, since if there is no diameter, there is no circle to speak of. If we go one step further, we can choose a diameter of length 1 in any unit of measure, and their circumference would then be exactly pi units in length. So technically, we can construct pi physically up to a certain accuracy if we can construct a circle of diameter 1 with certain accuracy. Not easy to do, but theoretically possible. In fact, for any additional length of diameter that we add, we would expect to see the same length times pi get added to the length around the circumference. So if we add another unit 1 to d, example, let's say d is equal to 2, we would have to add another pi units of length to c. Example, the circumference would then be equal to 2 pi. The same exact relationship holds in reverse, which if we arrange the equation again to be d is equal to c divided by pi, this time add a little bit to the circumference of a circle, you get a proportional amount which is divided by pi added to the diameter. But things get more interesting if we take this to the extreme. Let's assume we have a rope that encircles a whole planet, like Mars. Mars has a diameter that is a little less than 7,000 kilometers in length. Mars also has a circumference a little more than 21,000 kilometers around. In meters, that's a diameter of 7 million meters and a circumference of 21 million meters. That's a lot of meters. Now let's take that rope that goes around the whole planet and add 3 meters, or about 10 feet of rope. So that's 3 meters out of 21 million meters of rope. Not much at all. That's around the height of 2 human beings. When we add that 3 meters, that means you would approximately add 1 meter to the diameter of the loop made by the rope, or half a meter at each side of the diameter. But that means that the rope encircling the whole planet now has a half a meter gap, or 1.5 feet, around the entire world because we've added just 3 meters of length out of 21 million to the circumference. That's astonishing. And of course, the exact same outcome would happen if we also repeated this experiment with the theoretical rope around our whole galaxy. The number pi captures a fundamental invariant for circles in space. We can also talk about how to calculate pi. There are multiple formulas and algorithms that are used to determine the digits of pi with the aid of computers. These methods include using calculus or an infinite series, and there are many more with differing efficiency and speed of calculation. One particularly interesting formula was discovered relatively recently in 1995 called the BBP formula. And it's interesting because it can be used in conjunction with other formulas to compute any digit of pi without having to compute the preceding digits. That's odd and surprising. Lastly, I will give one example where pi appears out of statistics. You can take an experiment like flipping a coin and noting how it lands, heads or tails. You can conduct this experiment by flipping the coin multiple times in a row, such as 100 times. You can then take note of the number of times an outcome like heads appears out of all of those coin flips. If you repeat this experiment multiple times, you can graph the results to show how many times heads appears for each round of flipping. This experiment and many other related statistical experiments produce a graph called a normal distribution or a Gaussian distribution, or commonly known as a bell curve. This kind of distribution is very common in nature and statistics. We can take the shape of that graph and model it mathematically as a basic function called a Gaussian function. Well, it turns out that if you take that basic form of this function and calculate the area under that curve, the answer turns out to be the square root of pi. So we started out by flipping a coin multiple times across many trials, and that produced a graph which in its basic form has an equation with an area having the value of the square root of pi. How odd and astonishing. Thanks again for tuning into this episode of Oddly Real. Remember, oddly real, really interesting.